In this recording on functions and graphs, I want to talk about inverse functions and verifying inverse functions. Suppose we have a function, let's say we have f of x equals x plus 8. And what I'm going to do is pick a few values for x, plug those values into the function and get the corresponding y values. Now keep in mind f of x is just the same thing as y. So I'm going to pick -3, -2, -1, 0, 1, 2, and 3. Excuse me. Now, if I substitute -3 into the function f of -3, -3 plus 8 gives me 5. If I plug a -2 in, -2 plus 8 is 6. Plug a -1 in, -1 plus 8 is 7. Plug a 0 in, 0 plus 8 is 8. 1 gives me a 9. 2 gives me 10. And 3 gives me 11. So I plug these x values in, and these are the corresponding y's I get. Now, let's suppose I have another function. Let's call it g of x. And we're going to let g of x equals x minus 8. And let's do a table of values for this particular function as well. But what I'm going to do is I'm going to use the values that I got for my y in the f function as the x's for the g function, and you'll see why in just a few minutes. So for x, I'm going to plug in 5, 6, 7, 8, 9, 10, and 11. So I'm just using these y values as the x's for this function. Now let's watch what happens. If I plug a 5 in, 5 minus 8 is -3. Plug a 6 in, 6 minus 8, -2. 7 minus 8 is -1. Plug an 8 in, 8 minus 8 is 0. 9 minus 8 is 1. 10 minus 8 is 2. 11 minus 8 is 3. Now, I want you to notice all of the values that make up the domain of the f of x value of the f of x function are the same values that make up the range of the g of x function. So your x's, keep in mind x, those are your domain values. Those are your input values. So the domain of f is the same as the range of g. Also, the values that make up the range of the f function are the same values that make up the domain of the g function. When something like this happens, what this means is that these functions are inverses of each other. Given two functions, f of x and g of x, the functions are inverses of each other if the values in the domain and the range of f of x can be exchanged to make up the domain and the range of g of x. If we're given two functions, how do we verify that one is the inverse of the other without going through all of the work of creating a table of values? Now, we could do that, but it would take a lot of work, and depending on the type of function that you have, it may be a little bit more complex than the example that I gave. So we need to find a way to verify if one function is actually the inverse of another. And the way we do that is by using compositions of functions. let f and g be two functions such that f composed of g of x, f of g of x, equals x for every x in the domain of g, and g of f of x equals x for every x in the domain of f. What does this actually mean? F of g of x means we're going to take the g function and plug it into the f function. And when we simplify it, if we get x as the simplified version of that, of the simplified answer, and if we do it the other way around, if we take the f function and plug it into the g function, simplify it and get x, this x is what's called the identity function. The function g is the inverse of the function f. And the way we denote it is by using f with a little -1 here. It looks like an exponent, but it's really not. You don't do any calculations with it. It's just notation. The way you read this is f inverse. Thus, f composed of f inverse of x, or you can just say f of f inverse of x equals x, and f inverse of f of x is equal to x. The domain of f is equal to the range of f inverse, and vice versa. So this is just the mathematical definition of an inverse. So let's look at how we actually use this definition. It makes a lot more sense when you can see some examples. So here's my first example. Find f composed of g of x and g composed of f of x, and determine whether the functions f and g are inverses of each other. So my f of x, I'm going to call that 4x plus 9. And let's let g of x equal x minus 9 over 4. So first, let's find our f of g of x. So what does that mean? That means to take our f function, and everywhere there's an x, I'm going to have to plug something in. Well, what do I plug in? I plug in my g function, g of x. My g of x is x minus 9 over 4. So what goes here in place of the x is x minus 9 over 4. Now I need to simplify this. Notice I have a 4 here. This is understood to be 4 over 1. And then I have this 4 in the denominator, so they cancel each other out. And that leaves me with x minus 9 plus 9. But notice our 9's cancel, -9 plus 9, leaving x. So f composed of g of x simplifies to x. Let's look at our g of f of x and see what we get. G of f of x means we take our g function, and everywhere there's an x, we're going to have to plug something into it. Well, what do we plug in? We plug in our f function. So our f function is 4x plus 9. When we simplify this, now notice in the numerator we have a 4x plus 9 minus 9. So we don't need those parentheses anymore. The 9's will cancel. We get 4x over 4. Those 4's cancel. And we get x. Since f composed of g of x is equal to x, and g composed of f of x is equal to x, f and g are inverses of each other. So this is how you actually verify it. You have to get the identity function. You have to get x both ways in order for those functions to be inverses. If you were to take some values, some x values, and plug them into your f function, and get the corresponding y's, you could go back and see that those y's that you get if you plug them in as x's into the g function, you would get the x's, the y's from this value would give you the x's for your f function. Let's look at another example. So same directions, find f composed of g of x and g composed of f of x and determine whether the functions f and g are inverses of each other. This time I'm going to let my f of x equals 5x minus 9 and g of x is equal to x plus 5 over 9. F composed of g of x, we take our f function, and everywhere there's an x, we need to substitute the g function. The g function is x plus 5 over 9. So now we need to simplify this. Now notice, here we're not going to get anything to cancel like we did on the last example. This is a 5 and this is a 9. This 9 cannot be canceled with this 9 because this is not multiplication. This 9 is a separate term that's added to this. So all I can do is distribute my 5 through parentheses here. So I get 5x plus 25 over 9 plus 9. Now this 9 is a separate term. Before I can combine it with this fraction, I need to rewrite 9 as a fraction and get a common denominator. Keep in mind 9 is 9 over 1. To rewrite 9 as a fraction so that it has 9 as a denominator, it's 81 over 9. So it's just basic arithmetic. So 9 goes, 1 goes into 9. 9 times 9 is 81. So that's where we get that from. Now our denominators are the same. So we combine our numerators. We get 5x plus 106 over 9. Now, there's nothing I can do to this. We can't simplify this. F composed of g of x is not equal to x. Since f composed of g of x is not equal to x, there's no need to check the g of f of x, because in order for these functions to be inverses of each other, the composition has to equal x both ways. This one already failed, so there's no need to go through the work on this one. Let's look at another example. Oh, and once again, f and g are not inverses of each other. Example 3. Same directions. Find f composed of g of x and g composed of f of x and determine whether the functions f and g are inverses of each other. So this time we're going to use a radical. Let's let f of x equal the cube root of x minus 4 and g of x equals x cubed plus 4. So the steps are the same. F composed of g of x, we need to take our f function, and everywhere there's an x, we're going to plug in our g function, which is x cubed plus 4. Now under the radical we have an x cubed plus 4 minus 4. These 4's will actually cancel each other out. So we get the cube root of x cubed. But if you remember from algebra, cube root of x cubed, your root and your exponent will cancel each other out, and this is really just x. The cube root of x cubed is x. But now we need to check it the other way to see if our g composed of f of x gives us the same thing. So we take our g function, and everywhere there's an x, we're going to plug in our f function. Cube root of x minus 4 cubed plus 4. So here we have the cube of a cube root. Once again, the radical and the exponent cancel each other out, and we're left with just what's under the radical. So we have x minus 4 plus 4. When we simplify this, we get x. All right, so once again, f and g are inverses of each other. So to verify whether or not two functions are inverses of each other, you do a composition of functions both ways, and you have to get x. You have to get the identity function both ways. If that happens, they are inverses. If it does not happen, then they're not inverses.